All right, before we check our homework today, let's take a quick look at some of the terms that we learned over the last couple of days. The first one that I want to look at is vector versus scalar. Vector cereal versus cornflakes or Fruit Loops. What's the difference between a vector and a scalar? What does vector have that cornflakes doesn't have? Yep, direction. So vector has both direction and magnitude, whereas a scalar has only magnitude. Good. Now, we learned a number of different terms over the last couple of days. We're going to phrase the review a little bit differently today. And yesterday, I asked you to define certain terms and then tell me whether they were vectors or scalars. Today, I'm going to say, I want you to list for me examples of vectors and scalars. So of what we did over the last couple of days, those terms, I want you to tell me one of them that's a vector quantity. Who can tell me one of them that's a vector quantity? Remember those terms we did? Distance, position, displacement, speed, velocity, time. Tony? Position is a vector. Good. Who remembers the symbol for position? Yep. Good. D with that vector sign over it. That little vector sign reminds us that it's a vector, right? The little half arrow reminds us that it's a vector. All right. Somebody give me an example of a scalar now. Jack, you got an example of a scalar for me? Good. Distance is a good example of a scalar. And what's the symbol for distance? There's actually two of them, actually.
Small d and delta.
Good. Small d, or we could use delta d as well. What we have to be careful of is that we don't put the little half arrow over, right? Because we're talking about scalars. Okay, you correctly told me that they were both scalars. We got to remember not to put the vector sign over it to remind us that these are scalars. Okay, something else. I don't care whether you give me a vector or scalar here. Just tell me what it is here, guys, okay? Give me another one there. Let's say, let's go with Aiden. You got another example of a vector or scalar, Aiden? Velocity, okay. What is it, a vector or a scalar? Good. And what's the symbol for velocity? Good. V with the vector sign or the half arrow over top. Good. Give me another one. Vector or scalar, doesn't matter. Time is at what? Good. Time is a scalar, no direction associated with time. The symbol for time would be T or, yeah, T or delta T. T usually refers to when you have an instant in time. It is 10:24 a.m. right now. Okay, that's a moment in time. Okay, that would be T. Delta T would be, it has been 9 minutes since the beginning of class. Okay, a time interval would be delta T, right? A difference in time or a change in time. We got a couple more, I think. Position, distance, velocity, time. We're doing it in a different order, so it's kind of hard to remember which ones we have left and which ones we don't, but got another one for me? Speed, vector, scalar. Good. And what's the symbol for speed? Good. Without the vector sign over it, because that would be velocity, right? I think we got one more, don't we? Yeah, we do. Yeah, I remember what it is. Yep. Right. Displacement, good. And is that a vector or scalar? Good. And what's the symbol for displacement, Atlanta? Good. Delta D with a little thingamajig over top of it. I don't care what you call it, right? We all know what we mean by something over top of it there. Good. Good. Okay, let's look at this, this, and this. They're not exactly the same thing, but they're closely related. Close enough that they all have the same standard units. What would the standard units be for all those things that I have circled in green there? What are the standard units there? Carrie, what's the standard units there? Good, meters. Now, we did a problem yesterday where we used kilometers, right? We can use kilometers sometimes. Okay, there are times when we've got to use meters. There are times when we don't have to use meters. If in doubt, if you're not sure, then just use meters because it always works, right? Velocity and speed kind of also go together here. They're not exactly the same thing, but they're close. What would the standard units be for velocity and speed? Standard units for velocity and speed. meters per second. Good. Which takes us to the last one we have here is time. What would the standard units be for time, Seth? Seconds. Good. So meters and seconds, of course, give me meters per second. Good. So what do we got here? Distance and displacement often go together, right? Velocity and speed often go together. Distance and displacement, in fact, are often the same number. Displacement has a direction, distance doesn't. But as far as the number goes, they're often the same value. Tell me when they are the same value, distance and displacement, and when they're not the same value, distance and displacement. Let's go with Jordan on this one. When are distance and displacement the same value? When are they not the same value? Okay, we need a little bit more than that, right? Okay, good. And when you change direction, they're different, right? So for instance, if I walk 3 meters toward the back of the room, and then I walk 2 meters toward the back of the room, what's my distance covered? 5 meters. What's my displacement? 5 meters toward the back of the room, right? Needs a direction, okay? Same direction, the values for distance and displacement with the same values. Now let me walk 3 meters toward the back of the room. 1, 2, 3. Now let me turn around and walk 2 meters toward the front of the room. What's my distance covered? 5 meters. Still walk 5 meters. What's my displacement? 1 meter toward the back of the room. Make sense? When I go in the same direction, distance and displacement have the same values. When I change directions, then those values are going to be different values. That make sense? All right. Velocity and speed also go together. Oftentimes they have the same value. Again, velocity has a direction, speed doesn't. But sometimes they don't have the same value. When do velocity and speed have the same value? When do they not have the same value? Jordan, when do velocity and speed not have the same value? Good, good. When I change direction, good. So for instance, if I'm driving to Edmonton, 350 kilometers, okay, my average speed to Edmonton will be the same as my average velocity. It's a pretty straight line there, right? I'm not really changing direction dramatically. Okay, so my average speed will be the same as my average velocity. But if I'm running around the track outside, which all of you are going to be doing next week because you're all coming to the cross-country meeting at lunchtime today and signing up for cross-country, right? You're running around the track outside, your average speed will be 12, 13, 14 kilometers per hour as you're running around the track. Your average velocity when you're finished for the day will be 0 because you'll end up back where you started. Your direction changed. So velocity and speed become different values. Okay, good? All right. We learned a couple equations yesterday. Well, really one equation with a bit of a modification. It was the equation for average speed. What was it? Speed was, let's go with Leah here. Speed was, good, delta D over delta T. So distance over whatever the time interval was. Velocity, on the other hand, real close to the same thing, right? But it's not distance over time. Velocity would be displacement over time. Remember how we define velocity? It's the rate of change of position. Rate has a time on the bottom, change in position or displacement on the top. Good? All right, one more little thing before we check over our homework here. Sometimes we had to find the displacement to put into that equation. Sometimes we might be given the displacement. Question might say, here's the displacement, here's the time, what's the velocity? Well, that's an easy question if you're given those values, right? Sometimes you might need to find the displacement first. There's 2 ways to find displacement, depending upon whether you're given position or whether you're given displacements already. For instance, I'm 2 meters from the front of the room. I walk. Now I'm 6 meters from the front of the room. Was I given displacements there or positions there? Where I was or how far I've gone? What was I given? Positions, right? I was there and now I'm there. Those are 2 different Those are two different positions, right? What do I do with those values to get the displacement? I was 2, then I was 6. What do I do with those two values to get the displacement? Add or subtract? Add them. So is my displacement 8? I'm here, 2 meters from the front of the room. I'm here, 6 meters from the room. Did I move 8 meters? What do I got to do? Yeah, good. Hold on, stop. Don't get ahead of me. If it's position, you subtract them. Final position 6 meters minus initial position 2 meters gave me a displacement in that case of 4 meters, right? Let me give you another one. Okay, this time I'm going to walk 2 meters. Now listen carefully. I'm not at 2 meters. I'm going to walk 2 meters. Then I'm going to walk 6 more meters. Were those positions or displacements? I don't know where I was. I didn't say where I was. I said how far I walked. I was given 2 different displacements. How do I find displacement from 2 different displacements? Yeah, Jordan? We add them up, right? We're going to call this D1, not DI, because then it's going to get really confusing with position, right? D1 plus D2. And there might be 14 displacements you got to add up, right? In this case, we only had 2. So it's either subtract positions or add displacements to get total displacement, and then you simply divide that by time to get velocity. Good? Okay, one more quick little thing, actually. I said that was going to be the last thing, but I want to do one more quick little thing because this is going to help us with some of the questions that we're going to do a little bit later today. Sometimes you might be given velocity, and you might need to find displacement or time from that equation. How would we rearrange this equation to solve for this? To solve for displacement, or how could we rearrange that equation to solve for time? Let's remember some rules here, okay? We learned back in grade 6, I think. You were in algebra. I think you started grade 6 a little bit. If we want to get d by itself, delta d, I should say, by itself, then we have to get rid of everything that's attached to it. We have to first make sure delta d is on the top, which it is, and then we have to get rid of everything that's attached to it. What's attached to the delta d right now? Yep. It's attached to t. So we got to get rid of the t, right? How do we get rid of the t? If it's d divided by t, we're going to get rid of the t by doing what? Multiplying it, right. So let's say delta d, okay, multiply both sides by t. Here, let's do it up here. What happens on the right-hand side? The t's cancel. On the left-hand side, we're left with v times t. So my equation becomes d is equal to v times t if we're looking for displacement. Good? What if we're looking for t? What if we're looking for t here? First thing you got to do is get it on the top, because it's not on the top right now, it's on the bottom. Get it on the top. How do you do that? Who haven't I called on today? Who haven't I called on today? Let me just look through my list here. Who haven't I called on? Allie, I haven't called on you, I don't think, have I? No? What am I going to do to get t on the top? It's d divided by t. No, close though. I'll give you a hint, guys. I haven't solved for t yet, but I have got t on the top already. I multiplied t by v, right? T's on the top right here. So now what do? Well, what's attached to the t? V. Let's get rid of the v. How do I get rid of the v? Divide it. So it becomes t is equal to d divided by v, right? The d comes down by dividing. Really what I'm doing there is dividing both sides by d, but it has the, by v I should say, but it has the effect of that. So there's the three forms of my equation. V equals D over T, D is equal to V times T, T is equal to D over V. Did you guys ever learn that triangle method? You guys ever learn that? In Science 10 or something like that? Yes? Forget it. Forget it. I hate that. I hate that triangle. If you've learned it, that's too bad. I'm sorry. Okay? If you haven't learned it, good. You're better off if you haven't learned it. I hate that because although it works for three variables like this, when we get into more complicated equations, we've got to be able to do algebra. Okay? We've got to be able to do that. If you're having trouble with that right now, that's okay. I'll help you with it, okay? But we've got to be able to do that, not that silly triangle thing that works only with a couple different equations. All right. Homework last night. Page 10, number 1 to 7. What we'll do when we check over homework each day is essentially what we're going to do today, and that is just ask you which questions you'd like to go over. If we need to go over all 7 of them, that's fine. But if everybody got 6 out of 7 correct and understands 6 out of 7 of them, we don't need to waste time going over those 6 questions, right? So what I'll do is poll you. Just do a quick straw poll here. Okay? If people need them gone over, we'll go over. If people don't, then we won't. Okay, so I'll ask you right now, which question or questions out of these 7 questions do we need to go over? Just put up your hand if you've got 1 or 2 or 3 or 6 that we need to go over here. 7, yeah. Any others? 4, 6, I guess 4, 6, 7. Carrie? 4, 5, 6, 7. Is that it? Going once? Going twice? 1, 2, and 3 are okay? All right, 4, 5, 6, 7 it is. All right. Question number 4 says, draw a seating plan using the statements below. Chad is 2 meters to the left of Dolores. I know people were doing this yesterday during scheduled help, and there was a number of people that started too far to the left or too far to the right, and it's like, I ran out of space. You think you got it, you know how to do this, and then you just run out of space on your page. I hope that doesn't happen to me. We're going to put Dolores right here. Chad is 2 meters to the left of Dolores, so we're going to put Chad right here. 2 meters to the left of Dolores. Okay, not 2 meters to the right, 2 meters to the left. Then it says Ed is 4.5 meters to the right of Chad. We're going to put Ed over here. Now, there's 2 ways that we can label Ed's position. What's one of those ways that we can label it? What's one of them? Yep. I can say it's 2.5 between Dolores and Ed. Good. That's the way that I probably would have done it. But what's the other way that I could have done it? Literally from the question. Okay, I saw a number of people did this yesterday. Tony, you might have did this yesterday. Did you label it differently? Anybody say 4.5 from here? Yeah. So either way is fine, right? Either way to label that is absolutely fine. Okay, so what do we got here now? Greg. Greg is 7.5 meters to the left of Chad. Somebody want to draw in Greg here? When I was in school, everybody always wanted to come up to the board and participate. Nobody wants to do this? Okay, right. So we're going to draw in, who are we on here? Greg? Greg's 7.5 meters to the left of Chad. We'll make you do a couple of them. We're not going to let you off the hook with just one of them even. Okay, 7.5 meters to the left of Chad. That looks good. Is that right, guys? Okay, what's the next one? Hannah is 1 meter to the right of Ed. Good. Is he right? How many people got the diagram that looks like this? Excellent. Excellent. It doesn't seem crazy hard, hey? Now, I know a lot of people, as they were doing it themselves, are kind of a little bit puzzled by it at first, but once you've seen it, once you've done it, it's not so bad. Thank you, Aiden. What's the displacement of a teacher who walks from Greg to Hannah now? From Greg to Hannah, all the way from here to here. What's the displacement? Go ahead. It would be 13 meters. Add them all up, right? What would be the distance that the teacher walked from Greg to Hannah? Sorry, Sorry, you're wrong. The distance is 13 meters. The displacement would be 13 meters to the right. And I think it said right, left. Yeah. So we wouldn't say east there because we don't know that right is necessarily east. We just know it's to the right there. Okay? 5. This one I helped somebody with this one yesterday. A little bit tricky. A little tricky here. A person's displacement is 50 kilometers to the west. What's his final position if he started at 5 kilometers to the east? Let's make east positive first. Okay. 50 kilometers, what is that? Is that position or is that displacement? Position or displacement? Zach, isn't it? Right? Zach, yes. Person's displacement is 50 kilometers. That's displacement, right? Okay, so that's going to be delta D. We're going to make that negative because it's west, right? Make sense? What's his final position if he started at 5 kilometers to the east? I'm going to write this down, 5.0 kilometers. Make it positive because it's east. But what do I write down beside it? What's his final position if he started at 5 kilometers to the east? That 5 kilometers, is that a position or displacement, Tony? That's a position. Which position is it? Is it initial or final? Good. It's initial position. That's where he started. What am I looking for? Bart, what am I looking for here? Good. Looking for DF. Now, usually I subtract final minus initial to get displacement, right? I can still do that. Except that it's actually this that I'm looking for. So I got to get rid of the DI. I got to take it to the other side somehow. How do I take it to the other side? What do I have to do to take it to the other side there? Add it. Good. Subtract it on the right side, add it on the left side. So it becomes delta D plus DI equals DF. Delta D was negative 50. DI was positive 5.0. So it becomes negative 45 kilometers. And what does that negative mean again? Tyler, what does that negative mean there when we get negative 45? East. East? Right, west. You know, I do that all the time. You know, it's just a slip of the tongue, right? Okay, we know what you meant there. 45 kilometers to the west. Right? I think we had 2 more questions we need to do, right? 6 and 7? Yeah, 6 and 7. Question number 6 says, using an, I'm not even sure how to say that, autuck, which is a type of seal screen racket, 2 children play catch, standing 3 meters apart. Okay, it's labeled for us here in the picture. The child on the right tosses the ball to the child on the left, then moves 5 meters to the right to catch the ball again. So, what's happening here? The ball is going 3 meters here, right? Then, this person on the other side, she hits it back to this guy, but this guy is now over here. So now the ball is going, how far is the ball going the second time? How far is the ball going the second time, Bart? Good. Okay, what a lot of people will do there is say it's going 5 meters. It isn't. It's going to 5 meters plus the 3 meters that was originally in between it. Determine the horizontal distance and displacement the ball travels. What's the distance this ball traveled? Remember, distance is a scalar, right? Distance is a scalar. Jarrett, how far did this ball travel? What's the distance? Good. So we're going to say delta D is 11 meters. And what's the displacement? What's the displacement, Ryan? Good. No, it's not 8, actually. No, distance is 11. Remember, displacement is a vector, so direction matters. Is this a displacement or a position? Displacement, right? So we're going to say we're going to add the displacements, right? Neg 3 meters plus positive 8 meters gives me 5 meters. So the distance the ball travels is 11 meters. The displacement is 5. Why is the displacement 5? Because the ball started right here and the ball ended right here, right? So in the end, we could have just looked at this picture and said the displacement was 5. Final position minus the initial position. Right? And one more, question number 7. It says, below is a seating plan for the head table at a wedding reception. Relative to the bride. Remember we talked about relative, a reference point, last couple of days? Okay, when we're measuring a position, it has to be relative to something, right? I forget who the people we used in our example or on the first day of, the dance and whatever. Atlanta was one of them, right? Who was the guy? What was it? He was so traumatized that he decided not to come today. It's important when we're talking about a position to say relative to what? To have a reference point, okay? Relative to the bride. Well, the bride's the most important person at a wedding, right? So let's measure everyone's position relative to the bride. Let's describe the positions of the groom, the best man, the maid of honor, and the flower girl. So here's the bride right here. Let's put the bride in red there. What's the position of the groom relative to the bride? What's the position, Lewis, of the groom relative to the bride? 0.5 meters? No, not quite. You're close. Good. 0.5 meters to the right, right? Because position not only needs a reference point, but it also needs a direction. 0.5 meters to the right. Good. Okay. What about the best man? The best man. Yeah, go ahead. Okay. Good. 0.75 to the left. Isn't the best man, isn't he usually on the groom's side? I don't know. I got married once. I can't remember where the best man was sitting. I think it was beside me. Beside me, not beside my wife. But it seems odd that the best man would be over here. But anyways, okay. You're right. Anyways, Aiden, it's 0.75 to the left of the bride there. Maid of honor. This is a little bit tougher. Maid of honor is where? Who thinks they're really smart here? Tony thinks she's really smart. I think she is too. So let's go, Tony. Good. She's 1.25 meters to the right of the bride. Excellent. And finally, the flower girl. I guess the ring boy is not important here. That's the other thing. Wouldn't the ring boy and the flower girl be sitting beside each other, these two little kids? Poor ring boy off here with the maid of honor. Shouldn't they be sitting beside each other? Just seems like an odd wedding to me. I think it's doomed. I think it's destined for failure, this wedding. Poor organizational skills, for sure. Okay, where's the flower girl? Yep. Good. Yep, 1.5 meters to the left of the bride. We're good there, guys? Yes? Good, good. Let's do one more example now of the stuff that we did yesterday, the whole speed and velocity thing. This is 1.7 on page 37. You don't need to copy the question out because it appears in the textbook. Just reference it in your notes. Just say, example 1.7, page 37. But when we do the solution, remember to please copy out that solution. Give you a chance to read that question, okay? Okay, so give you a chance to read through this, see if anything jumps out at you, anything odd, any questions. I had one good question, one that I kind of thought of myself. Find the average velocity of a student who jogs 750 meters east in 5 minutes, does static stretches for 10 minutes, then runs another 3 kilometers in 30 minutes. There's a couple of different things with the units here that kind of stick out to me that I don't really like. Okay, the first thing is minutes. I don't like minutes. Okay? We can use minutes when we're calculating speed. We can, but it's just different. So I don't like it. I'm going to get rid of them. I'm going to circle the minutes there to remind me that I want to change those into seconds. The other thing that I noticed with the units is what? This is even more important than the minutes thing, though. Yeah, Aiden? Yeah. Here we have meters. Here we have kilometers. You can use kilometers, but you can't use meters and kilometers in the same question. Okay. I'd rather use meters, but if we use kilometers in this case, it's okay. We just got to make sure we're in the same units for both. Okay, so let's write down some givens here, okay? He jogs 7, let's define east as positive, which makes sense because everything's going east, right? He jogs 750 meters to the east. Is that a position or displacement? Is that where he is or how far he's gone? He jogs 750 to the east. Where he is or how far he's gone? How far he's gone. That's displacement, isn't it? So let's say delta D1 is 750 meters. We'll just make it positive 750 because we already defined east as positive. The time interval that it took him to run 750 meters is 5 minutes. Which, remember, I want to convert that because I don't like that minutes thing. I can convert minutes to seconds. This is one of the easier conversions that we do. Minutes to seconds, 80? Yeah, 60 seconds in a minute. Multiply by 60, we get 300 seconds. All right. Then he does static stretches for 10 minutes. What's his displacement while he does static stretches? 0. He doesn't move at all. Right? He moves his arms and his legs, but his displacement is 0 because his arms and legs end up where they started, right? Time interval for the second interval there is 10 minutes, which is going to be 600 seconds. 10 times 60 is 600. He runs another 3 kilometers. Position or displacement? He runs another 3 kilometers. Position or displacement? Displacement, yeah. And it's going to be positive as well because it's to the east. We're going to call that D3. For the first time now, we've got 3 displacements, although one of them 0. And the time interval there is going to be 30 minutes. Oh boy, 30 minutes. 3 kilometers in 30 minutes. You know what he should do? This guy should run cross country so he can pick up the speed a little bit. 30 minutes for 3 kilometers is pretty slow. Okay. If he ran cross country, I guarantee you he'd be faster than that. Okay. Maybe not the first day. That's okay. You can come out next week on the first day and walk if you want. You'll get faster than this guy, I promise. That's going to be 1,800 seconds, right? 30 minutes times 60 is 1,800 seconds. Okay. Yeah, Lewis? Yes. Thank you for noticing that. I circled that to draw my attention to it up here, but then I went and forgot down here, right? Let's change kilometers to meters. What is 3 kilometers? Yep. 3,000. Multiply by 1,000, right? Okay. So remember what I said the equation for velocity was? Delta D over delta T. Here's what a lot of people will want to do for this question, but I'll tell you right now, it's wrong. People will say V equals D over T, get a V. V equals D over T, get another V. V equals D over T, get another V, and then average those together. That's wrong. The only time that would ever work is if these time intervals were the same, and that's not very often. Don't do it that way, because it's wrong. You want to find the average velocity? Let's say V equals D over T. What's the total displacement? Do we add them or subtract them? We add them. 3,750 meters, right? 750 plus 0 plus 3,000. What's the total time? Tony? 2,700 seconds, right? Add the displacements, add the times, go 3,750 divided by 2,700. What do we get for that? 1.39. I would actually round to 1.4 meters per second. You guys know from Science 10 about significant digits? Who has learned about significant digits? Okay. We're not going to lose any sleep over that right now. We'll talk about that more as the semester goes on. But if those of you who learned about it, we'd go back to our original data here and say 3 digits, 2 digits, 3 digits, 2 digits, 3 digits. Final answer should be rounded to 2 digits, the least number of digits in our data. Okay, again, if that confuses you a little bit right now, don't worry about it. We'll talk about it lots more as the semester goes on, okay? Good? Look at that, perfect timing. What time did I say we're going to stop? About 11 o'clock. What time is it? About 11 o'clock. Isn't that perfect? Okay, here's your homework, guys. You're going to have 2 questions on page 37 for homework. In addition, you're going to have a worksheet. So there's 2 questions there. There's 4 questions on the worksheet. You only have 6 questions for homework. And you may get a little bit of time a little bit later on to work on it. Certainly in scheduled help, you get some time. So you may have nothing or very close to nothing by the end of it. Okay. That's it.